Hi, thanks for watching this video. Here we're going to talk about thermometry, how thermometers measure temperature, and also the errors that are typically encountered when trying to measure temperature. When you make measurements of temperature, you want to make sure that your measurements are accurate and precise. That means that we want to minimize exposure errors. With thermometers, thermometers work on the principle that air surrounds the thermometer, and as a result, energy is transferred from the atmosphere to the thermometer. So our thermometers are complete immersion thermometers. They're surrounded entirely by the atmosphere. To get good measurements, we have to have good thermal contact between the thermometer sensor and also the environment. An analysis of the exposure errors that result from improperly sighted thermometers, we need to take a look at the thermal heat flow or heat balance of the thermometer and its surroundings. How is energy transferred to the thermometer, and how is energy transferred away from the thermometer? And if you go back to your basic meteorology, remember that there are three ways that energy can be transferred in the atmosphere, and that is through conduction, convection, and radiation. Conduction is the thermometer in contact with its mount and other structures. So in this case, energy is transferred by touching the mount and other structures. Convection means air flowing by the thermometer and carrying heat away or energy away. And then finally, radiation is where either infrared or solar radiation, electromagnetic radiation, is impinging upon the thermometer. And as that occurs, energy is transferred. With our analysis of exposure errors, we're going to ignore the conductive heat flow. In other words, we're going to assume that we did everything that we can to insulate the thermometer from its mount, and therefore we really don't have any conductive heat flow. We're going to look at the balance between heat lost by convection and heat gained by radiation. In this case, when we reach steady state, we can solve this equation. I kind of jumped a few steps here, but the temperature you see at the bottom is the temperature that's measured by your thermometer, the temperature of the thermometer, that's TS, and then TA is the air temperature. If that difference is zero, then your thermometer is measuring exactly the air temperature. That doesn't always happen. The thermometer or the sensor temperature is different than the air temperature, and that is your exposure error. On the right-hand side, there are a lot of factors that result in the exposure error. And that is, you see alpha and also R. Alpha sub S is the sensor absorptivity. How well does it absorb solar radiation, or for that matter, infrared radiation? R is your solar radiation, and underneath the square root, you see D, which is the diameter of the sensor, and then in the bottom of that square root, you see VA, which is the airspeed. Pi, of course, is a constant, and then C is a constant for the particular thermometer. If we analyze this equation, we can see that our difference between the sensor temperature and the air temperature is small when things on the right-hand side, when values on the right-hand side are small. So that means solar radiation, R, needs to be small to have a small error, small temperature difference. Also, absorptivity, alpha sub S, needs to be small. Absorptivity is the ability for the sensor to absorb solar radiation. One way to prevent the sensor from absorbing solar radiation is, number one, put it in the shade. That reduces R. And number two, paint the thermometer white or have it in a white shelter that reflects solar radiation. The other factors in the square root D is the diameter of the sensor. If you have a large sensor, then it's going to have larger errors. Smaller sensors are preferred. And then finally, VA in the bottom. When VA is big, the right-hand side of the equation is small. That's the velocity of the air. So if you have good ventilation, if you have air blowing by the thermometer, that will reduce the exposure error and the difference between the sensor temperature and the air temperature. So to summarize, minimizing your exposure errors means that you need good circulation going by the thermometer to promote heat transfer through convection. Also, you need to protect your thermometer from radiative heat transfer, in other words, from solar radiation, by putting it in the shade, or if you have a shield, using that shield. And typically shields are painted white, so the absorptivity will be reduced and the reflectivity will be increased. And then finally, the last thing that you can do is buy a sensor that's small so that it reduces the error. People have come up with different ways to shield thermometers. Here's one case. What they use is a louvered device that allows air to flow through. Each one of those rings has a space in it so air can flow through. Also, this protects the thermometer from precipitation. If it rains on it, the thermometer will no longer be a thermometer, but it will act more as a wet bulb. Also, the shield here, the aspirated shield, protects a thermometer from mechanical damage if there's hail or birds or other things. And also it's painted white and the thermometer is on the inside of the shield, so that reduces the solar radiation. Also, this shield has a small fan, and the fan promotes the aspiration, in other words, the ventilation of the thermometer. In this picture, you can see that there's a little solar panel, and that little solar panel actually runs the fan, provides electricity for the fan. So the fan provides a steady airflow so that you don't have stagnant air that heats up. This enhances the convective heat transfer, and also it offsets any radiative conductive heat transfers. Another way to minimize exposure errors is through the use of an unaspirated shelter. And the unaspirated shelter that's been standard with the Weather Service for years is the Stevenson screen. Stevenson screens are used when there's no power available to power a fan, to provide electricity for a fan. Also, Stevenson screens protect sensors from mechanical damage. The thermometers are inside the shelter, and as a result, birds and hail and other things won't impinge upon the thermometers. And also, it blocks most radiation. It's painted white so that you have good reflection of solar radiation. The Stevenson screen is unaspirated, which means it works on the principle of airflow. Wind. The wind is blowing, and as the wind blows, it blows through the louvers in the Stevenson screen, providing good aspiration for the thermometers. So this shelter works really good on windy days, but when the air is stagnant or calm, then you might have an increase in temperature inside the shelter, and the actual temperature may be lower than what the thermometer is reporting. Radiation error tends to be the worst type of error that you can have with a thermometer. It's very common and it is significant. Your basic passive shield will block 80% of the incoming solar radiation, but also it blocks 80% of the airflow. Radiation error can be classified as either direct or indirect. Direct radiation error is when solar radiation impinges upon your thermometer. In other words, you don't put your thermometer in the shade, it's in the sun. That's probably the worst type of error that you can get. However, there's also indirect radiation error, and this is where your thermometer, your sensor, is protected. It's in a shield or shelter, but the shelter heats up and passes its energy along to the thermometer. How does the shelter heat up? Well, solar radiation will actually be absorbed by the shelter, even though it's painted white. So you still may have some error if your thermometer is in a shield or shelter. So those are some ways to minimize the exposure error of thermometers.